I'm Chen, and I'm working on the algorithm part of AI ops things. And in the recent years, I've been working on the algorithms. Anomaly detection is the first problem I'm trying to solve. So today, I'm going to tell about the algorithms we have developed to solve the anomaly detection problems. So in order to monitor the healthiness of a service, an engineer must collect some data to reflect the status of the system. And Google's SRE book suggests that you can collect 4 types of signals, and they are golden signals. These golden signals are latency, traffic, errors, and the saturation. After you collect these signals, you want to do some alerting, right? So alerting becomes another problem. From the perspective of the machine learning, anomaly detection can be categorized as a classification problem. But actually, this problem is quite unique. First, the abnormal data are actually very rare. So this will create an extremely imbalanced data sample among the data you have collected. Secondly, labeling is also very hard. It will cost a lot of time for an engineer to label a very large time series data, right? So here I would like to introduce a case here. One day, an engineer posted a picture to one of the colleagues in my team and asked that whether the curve in the red box, in this red box, forms a proper sudden drop. And I showed this picture to a lot of other engineers, and most of them agree that it is very hard to decide whether this is a drop or not. So these challenges has forced us to leverage more on statistical analysis and machine learning, especially unsupervised machine learning. So we have applied our algorithms on a number of golden signals in multiple systems in Baidu, and we have achieved more than 90% on precision and recall. Next, I will introduce the algorithm one by one. So let's start with latency. So when monitoring the latency of a system, we usually want to find an upper bound threshold for it. So if an observed latency value exceeds this threshold, the monitor system will send out an alert. To decide the latency, we want to collect a segment of the history data first. For example, if we will observe the latency value every 1 minute, then we can collect 1 day's data, and the history segment will contain 1,440 data points. Then we can compute the average and the standard deviation of the history data. And the threshold could be like this. So the threshold, usually you can set that as a x bar means the mean, and the s means the standard deviation. So you will set the threshold like this one. So this approach is widely used, and some people call it the 3 sigma approach, right? So sometimes this is also called sigma. So this approach actually has a probability background. It regards the latency signal as a random variable, and then assume it follows a Gaussian distribution. A Gaussian distribution actually is determined by 2 parameters, the mean and the variance. The mean can be estimated by the average of the history data, and also the square root of the variance can be estimated by the standard deviation in the previous slides. So based on the theory of Gaussian distribution, the probability that we observe a value greater than the mean plus 3 times the standard deviation is around 0.0013, right? So this is quite low. That's right. That's the reason that we believe that the observed value is more likely to be an anomaly. So we can actually generalize this 3 sigma approach in the following way. First, we assume that the signal variable actually is follows some kind of random distributions. Then we can use the history data to build the models of the distribution. Based on these distributions, we can compute the probability that the signal's value falls into some specific range. In most cases, we would like to find the upper bound threshold or lower bound threshold. For the upper bound threshold, we can pick the threshold t that the probability of x greater than t is very small. Here, actually, we have 2 thresholds. One is the probability threshold p, this one, and the other one is the signal threshold t, this one. So t actually depends on the probability distribution and also the p. So why should we use a detour to the probabilities instead of getting the signal threshold t directly? This is because that the probability approach has a number of benefits. First, the probability threshold P actually refers to the false alarm rate. So if you decrease this value, you can directly observe that the number of incorrect alerts actually decrease. And the quantity of the decrease usually matches your feeling. Secondly, when you select a probability threshold, it usually can remain constant for a very long time. In our experience, this time can be longer than at least 1 year. Then we can refresh the random distribution model periodically. For example, refresh the distribution every 1 month. And then the model, after the model is refreshed, the signal threshold T actually is adjusted automatically. Then you can get the automatic threshold algorithm. So the quality of the alerts now heavily depends on the wisely choice of the probability threshold P. Because P refers to the false alarm rate, we can actually choose P in the following way. Suppose the monitoring system generates 1 point every 1 minute, right? So in 1 day, there will be 1,440 points. And we want that the number of false alarm points is less than 1 in a day. Then the P is going to be around 0.007. Actually, we find that we just set it to 0.001 is enough. So now the probability threshold has been decided, and let's turn back to the estimating the random distribution. This is actually the core of the whole thing. When I use probability to explain the 3 sigma approach, I mentioned that the approach assumes that the signal follows a Gaussian distribution. You can use a real signal to test that. The figure on the left side is actually a trend line of the latency signal from a real system. The figure on the right side actually shows its distribution. The green patches here, the green patches, are the histogram of the signal. And also the red curve is the Gaussian fit line estimated from the signal data in the trend line. We can see that this fit line is very different from the histogram. So if I choose the signal threshold based on this Gaussian distribution, it would likely to be a bad one, right? So this is the reason that the 3 sigma approach, although it is widely used, but sometimes it still provides results in very bad threshold. So in statistics, the 3 sigma approach actually uses the parametric method to build a distribution model. The parametric method actually first assumes that assumes the signal actually follows a family of distributions. In 3 sigma, the distribution family is Gaussian. Then we estimate the parameter of the distribution family, and a specific distribution is obtained based on the parameters. But in this case, actually, we don't know in advance that which distribution family is suitable for the signal. So we have to try the non-parametric method. Here, I use a method called kernel density estimation. This method actually can estimate the distribution based on a finite set of data samples. Kernel density estimation expands every single data point in the sample as a kernel distribution K. So this one is the K. And then the final distribution, Fx, is just the mean of all the kernel distributions. Gaussian distribution is still a popular kernel distribution. That means that the kernel distribution of data point xi is a Gaussian distribution, and the mean parameter of this Gaussian distribution is just xi itself, and the variance parameter of the Gaussian distribution will control the smoothness of the final distribution. According to the theory, the best sigma is shown like this. So if you want to know why this is the best sigma, you can just refer to the Wikipedia page about KDE. So to be honest, I don't understand that deduction, so, so just use it, and all right. So we can see on the right side of the figure, I plot the patches to refer to the histogram of the signal distribution. And also this red line refers to the Gaussian fit of the distribution. And the blue curve actually here, we have a blue curve here, means the KDE fit of the distribution. And we can see that the KDE fit is much better than the Gaussian fit. Next, we have the probability threshold P, and also we have the random distribution model. So we can find the signal threshold T by computing the probability through the integration here, right? And the orange horizontal line in the right side of the figure here actually refers to the position of the signal threshold t. So we can see that this is not so fortunate because the t is obviously too large. So by reading the data in detail, we find that this is because the history data contains some abnormal points. For example, these two spikes, right? So, and these points actually push the threshold up. So we need to find a way to remove these abnormal points. So how to do that? We actually use a variation of linear discrimination analysis to remove these abnormal data points. In machine learning, LDA is an algorithm solving classification problems. Usually, we will provide a set of samples to the algorithm. Each sample has a feature vector and a label. The label will tell which class the sample belongs to. Then, the LDA algorithm will find the best classification plane in the high-dimensional feature space to classify future samples. In our case, each data point only has one feature, its value. So this is kind of easier. But we don't have the labels, so we don't know whether the sample set contains any abnormal points. And if the sample set does contain some abnormal points, we don't know how much of them. So we know for sure that if the data set do contain some abnormal points, their value must be large, right? So therefore, we'll come up with the following unsupervised version of LDA. First, we sort all the data points in the increasing order according to their values. And then we split the sorted sequence into two clusters. Suppose we split at position I, the left cluster contains the first I data points with smaller values, while the right cluster contains the minus I larger data points. And then LDA will compute a value called the scatter within cluster for this split. This value is just the sum of the scatter of both clusters. A cluster of a single cluster is just the sum of the square errors of all the points against their mean. Then we hope that the right cluster will contain all the abnormal data points and no normal points. But of course, we don't know how many abnormal points are there in the system. So we have to split the sequence at every possible position. This will ensure that the correct split will be covered. So because we split the sequence at every possible position, there will be a series of scatter values, each corresponds to a split position. Then we can draw a position scatter plot from the position scatter pairs. So the plot on the left side actually is this scatter position plot. The horizontal x-axis means the position and the y means the scatter value. We can see that there is a steep downward spike in the curve. According to LDA, the left side of this spike actually contains all the normal points, and the right side actually contains all the abnormal points. So we can develop an algorithm to find this spike based on the value of the scatter and also on the slope of the curve. Then the data points at the right side of the spike can be removed. After these abnormal data points are removed, we can apply KDE on the rest of the data points and then derive the signal threshold. The yellow line here is the threshold generated after the abnormal points are removed. So you can see that this yellow line is much better. So that's all for the algorithm for latency signals. Next, I would like to discuss the saturation signals. Because the algorithm for these signals is similar to that of the latency signal. Saturation signals describe the utilization of resources. Here, I would like to focus on the signals that are in the form of percentages. For example, CPU idle or memory usage percentage. Alerting on these saturation signals can serve two different purposes. In the first purpose, engineers want to receive a notification when the system is going to be overloaded, right? So they usually will set the threshold based on their own experience about the system and also the signal. In the second purpose, the engineers want to know whether the resource consumption is higher than normal state. If it is, there probably something going wrong inside the system. So anomaly detection in this purpose needs the help of algorithm. So actually, we can apply kernel density estimation on the history data of the signal to build a distribution model, and then derive the signal threshold. But the problem is that all the signals are in percentage, so they will fall in the range of from 0 to 1, right? If we apply Gaussian distribution as the kernel density, as the kernel directly, we might end up getting a signal threshold less than 0 or greater than 1. If this happens, then our algorithm just fails. So to solve the problem, we replace the Gaussian distribution by the beta distribution. A beta distribution is a random distribution family that specifically model percentage random variables. So it has two parameters, alpha and beta, and they are decided in the following way. First, we want that the signal value, xi, to be have the largest probability density. So the xi and the alpha and beta has this kind of relationship. And then we know that there is a free constant c here. So when c is small, then the beta distribution will have larger variance, and so that the resulting fx will be smoother. So we need to choose this c wisely. And according to our experience, we find that you can just choose the c between 100 and 200, and that's fine. Most of the signals will produce satisfying results. So now let's move to the arrow signals. The arrow signals represent the number of failed requests in a given interval. Because many systems actually produce sporadic failed requests when they are in the normal state, therefore, anomaly detection on this signal actually needs to answer this question. In a total of X requests, and we observe Y errors, is Y too large or not? If we set a threshold directly on Y, then the threshold will have to change with X, because our engineers believe that as long as the ratio of Y remains stable, the system is okay. So the straightforward idea is to make the ratio as a signal and then set a threshold on the ratio R. But this idea is actually problematic. If we regard the ratio signal R as a random variable, its variance will be larger when the denominator X is smaller. So we still need to set multiple thresholds for R. So here is an example. This figure actually has three subplots. The plot on the top refers to X, the number of requests per minute. The plot in the middle refers to Y, the number of arrows per minute. And also the plot at the bottom is the ratio signal. In the middle plot, we can see that the number of arrows increased significantly between the time 1400 and 1600. But the number of requests in the same range actually remains stable. This implies that something wrong in the system. So we want the algorithm to generate an alert here. However, if we want to generate the alert, the threshold on the ratio must be at the level of the orange line here. So if we do set such a threshold, you'll find that this threshold is lower than most of the ratio values around 800, this part. And also, this value becomes fluctuated when the number of requests drops to 0 in the second between 1800 and 2000 here. So the threshold would generate two false alarms here, and these two false alarms actually both relate to the value, a small value of X, right? So we have to deal with that. So we still leverage the probability distributions to solve the problem. Actually, the number of Y follows a binomial distribution with parameters X and P0. X refers to the total number of requests, and the P0 refers to the probability that a request will fail when the system is in the normal state. Binomial distribution describes a coin flipping scenario. Suppose we toss a coin for X times, the number of times that the coin ends up as a head will follow a binomial distribution. This is exactly the same as we observing Y errors in a total of X requests. According to binomial distributions, the probability that Y is greater than the observed value Yj is the sum of the binomial probabilities for all k larger than Yj. So the binomial distribution is determined by two parameters, X and P0. And we already have X, and the P0 can be estimated by summing all the Y's in the history, this one, and divide that by the sum of all the x. So this can be regarded as the probability that a system will generate an error in the normal state. So because the computation cost of binomial distribution is very large, when the x value is large, we can estimate this probability by a Gaussian distribution. And this will create the proportion z-test, this one. So in this formula, we can see that yi over xi is just actually the error ratio. And then we compare this ratio against p0, right? And then this difference is, and then this difference will time the factor square root of x, this. So for the same value of error ratio, smaller x will make this value smaller. So this actually compensates the fluctuation of error ratio when the x is small. So here I will show you the result here. Let's come back to the plots in the previous slide. And we can see that the two plots at the top still refers to the number of requests and the number of errors. But the plot at the bottom actually becomes the z-score. First, we can see that the z-score in the segment between 1800 and 2000 becomes very small, right? This is because that the request is nearly 0. So actually the time actually depresses this down, pushes it down. And then we can see that it would be much easier to find the threshold to report the anomaly between 1400 and the 1600, while at the same time, it would only report a few data points as abnormal around 800. So this is some of the sporadic points we will report. And here is much better. I want to emphasize here that the algorithms for error signals is very different from the previous two signals. For latency and the saturation, we employ kernel density estimation to build a single random distribution model. And then the signal threshold is derived accordingly. Here in the arrows, we actually use two kinds of signals. One is the request number of traffic signal x, and the other is the error signal y. Moreover, we do not compute the signal threshold. This is because we actually have a lot of distribution models. Every different value x actually creates its own distribution. So if we do need to compute the signal threshold, we will have a lot of the y, right? Threshold on y. So we believe that z-score is a better normalization of x and y comparing to their ratio. So setting the threshold on z is a better solution. So when detecting the anomalies for the error signals, we have used the traffic signal. Now I will discuss how to perform anomaly detection of the traffic signal itself. Most of the traffic signals actually will have daily fluctuation pattern. The signal value goes up during the daytime and goes down during the nighttime. Just like the figure at the right side, most engineers will believe that the red dot here in the first peak refers to a traffic drop, and it should be regarded as an anomaly. But the value of this red dot is much higher than the values at the valley of the curve here. So we cannot apply kernel density estimation to produce the fixed signal threshold. On the other hand, most of our engineers believe that the traffic drop is much severe than the traffic rise. So when they set the alerting rules, they will set a tighter threshold for drop and a looser threshold for the rise. Because of these two reasons, we decided to use a two-step approach for the traffic signal's anomaly detection. In the first step, we want to predict the correct traffic value based on the previous values, assuming the system is in the normal state. And then in the second step, we will decide whether the current observed value is abnormal based on the predicted value. So actually, we have tried a number of algorithms to predict the current traffic value. This actually seems to scatter in the spectrum. One side of the spectrum is smoothing, and the other side is periodic pattern mining. The smoothing approach assumes that the signal is composed of smooth baseline and a noise component. The mean of the noise is 0. The simplest method in this approach is just moving average. Moving average defines a sliding window and compute the average of the data points in the window, and then the average can become the predicted value. Exponential smoothing predicts the current point using a linear combination of the observed value of the current point and the predicted value of the previous point. This is essentially a linear combination of the observed value of all the points in history, and the weight of each point decreases exponentially with the age of the point. Both moving average and exponential smoothing cannot resist the impact of abnormal points because all the points are treated equally. Therefore, we adopt the robust linear regression algorithm to reduce the impact of abnormal points. Robust linear regression is a kind of auto-regression algorithm, like a REMA. The linear assumption requires that the points in the regression window to be almost linear, so the regression window must be short. And it also has the slow catch-up effect at the peak and the valley of the traffic curve. So the algorithm regards the turning points as anomalies. To solve this problem, we tried to perform robust nonlinear regression, but we were not able to get any satisfying results. Later, we find a paper using variational auto-encoding to detect anomalies for traffic signals. VAE can successfully handle the nonlinear nature of the signal, so its regression window can be much longer than the robust linear regression. These four algorithms can detect sharp rise and drop. In some cases, engineers also want to detect small but persistent changes. The smoothing algorithm will regard the small change as normal and quickly catch up with the change. So to detect such changes, we have to consider the periodic patterns of the traffic model. Hot winters is a special smoothing algorithm. It further splits the smooth baseline into a linear trend line and a periodic curve. But when it comes to the real data, we find that the real traffic signals have multiple periodic patterns. So, for example, the shape of workdays is different from the shape of weekends. So we have to explicitly perform pattern mining on the signals. Next, I will introduce robust linear regression, variational auto-encoding, and the periodic pattern mining one by one. These three algorithms perform quite well in our experiences. So we have introduced robust linear regression in the SREcon last year. Comparing to the traditional linear regression, the robust one tries to minimize the sum of the absolute errors. So this is the goal of robust linear regression. This is just the absolute error. And the traditional linear regression actually tries to minimize this. This is the square of the errors. So this is actually just a modification on the power of the errors. Because the abnormal data points have a very large errors, square errors will amplify the errors greatly and force the algorithm to get closer to the abnormal points. So we can see in the plot here, on the right side of this blue curve actually is the original signal. We can see that the red line is produced by the traditional linear regression, and the right side is pushed up. And what we want is the purple line here, right? So if we apply this algorithm to a longer one, we can see that the fitted line is this one, and it has a shape of zigzag shape. So by reduce the power of errors from 2 to 1, the impact of abnormal points are weakened. So robust linear regression will be more resistant to abnormal points. This is why the algorithm people call it robust. So here is the result. So this is the result on the signal containing regular upward spikes, right? And the blue curve refers to the original signal. The black curve refers to the prediction curve produced by moving average, and the red curve is produced by robust linear regression. The red curve stays at the bottom of the signal and is a much better baseline than the moving average signal. So robust linear regression can resist the impact of abnormal points to some extent, but the same property actually makes it slow to catch up when the signal turns a little bit sharper. The signal at the right side demonstrates this problem. In the figure, the blue curve is the original signal, and the red curve is the prediction produced by robust linear regression. The green box shows a perfect stride over the abnormal drop in the original signal, right here. So we can detect this drop. But soon after, a convex appears in the red box here. So the prediction line actually rushed over, and we will generate several excessively large prediction values. And these large prediction values would increase the risk to produce false alarms. The reason of the rush over is because that the algorithm cannot handle the nonlinear part of the signal. So it seems to be quite straightforward that we can replace the linear model with a nonlinear model, and then we can solve the problem. However, a robust linear regression is much harder than we expect. We actually try to add a square term into the regression equation, and the prediction results is really bad. So we resort to a neural network technology and find that the variational auto-encoder seems to be a good tool. The basic idea of VAE is that the size or dimension of the input is first reduced here to the hidden layer, and then restore back at the output layer. So because the dimension of the hidden layer is smaller than the dimension of the input and the output layer, this reconstruction process will likely remove the unwanted noise from the input signal, and then the reconstructed signal will be smoother. We tried a few variational autoencoder algorithm and find that the donut algorithm published in W 2018 is very suitable in dealing with the traffic signals. The output of the donut contains two values for each data point. One value is the mean, and the other value is the variance. And we can just use the mean value as our prediction value. So when using this algorithm, the width or dimension of the hidden layer, of this layer, is actually very important. A narrow hidden layer will produce a smoother output, and a wide one will produce a rough output. From our experience, we find that when the size of the input is around 2000, setting the parameter to around 1000 yields the best results. So here is an example of the resulting of the variational autoencoder. In this figure, the blue curve is the original signal, and the orange curve is the prediction. The signal actually shows a daily periodic pattern, but the days are a little bit different from one another. Furthermore, the signal contains sharp turns and quite a few spikes at different time spots, which are hard for robust linear regression to handle. But the prediction curve produced by VAE seems to be reasonable. So at last, I will introduce an algorithm to distinguish small and persistent drops. Robust linear regression and the variational autoencoder would easily catch up with the small drop, and it's blind with these cases. Therefore, we need a more delicate algorithm. Actually, it is also a very hard problem for a human being to recognize the small drop. The engineers must use a signal segment in history as the baseline, and then they can measure the gap between the baseline and the current signal. This means that the signal must be periodic. The period is usually a day, so the baseline will be the signal of another day that contains no anomalies. The problem in this approach is that there could be multiple daily patterns. For example, the pattern of workdays is different from the pattern of weekends, and also other holidays. What makes things worse is that many Chinese holidays do not have fixed dates in the calendar. So the standard of choosing the baseline is kind of complicated, right? Another problem is that the signal in each day will be at a different level in the height. The figure at the right side shows a signal in 7 consecutive days, right? And from Sunday to Saturday, we can see that some of them are similar in shape, but all of them are at a different level. Our idea is to extract the shape patterns from each day first, and then when detecting anomalies online, a pattern is selected and expanded to the correct level. So according to the figure, we can see that the level difference is not the only obstacle of shape extraction. The random noise in the signal also makes things harder. So we can see that there are random noises in the signal. So here is the solution. First, we reduce the impact of noises by transforming the signal curve into a cumulative curve in a day. So each point in the cumulative curve is the sum of the signal values starting from the beginning of the day, and the figure on the left side shows the cumulative curve over the 7 days in the previous slide. So these curves become much smoother than the original signals. And the last data point represents the total traffic in a day. So because the traffic signal in each day is at a different level, the last data points will be at different positions. So naturally, we can normalize a cumulative curve by dividing the data points in the curve with its last point. In this way, the right side of the cumulative curve are all at 1, right? Here. So it becomes very easy to distinguish the patterns. In the figure at the right side, we can see that the normalized curves clearly demonstrate 4 patterns. 1 pattern for Monday, 1 pattern for Tuesday, Wednesday, and Thursday, 1 pattern for Friday, and 1 pattern for Sunday and Saturday. This seems to be quite meaningful, right? And then, actually, there is a math behind this procedure. We can regard the shape as a multi-nully distribution. If we collect the traffic signal every 1 minute, there will be 1,440 data points in a day. So the shape will describe that, given a specific request, what is the probability that this request will appear in one of those minutes. So it's like tossing a coin, but the coin has more than 1,000 outcomes, right? So the normalized cumulative curve is actually the CDF, cumulative distribution function of the multi-nully distribution. If the shape of the 2 days are similar, it is equivalent to say that the 2 corresponding distributions are similar. The probability theory indeed has a measurement of the similarity between 2 distributions, and the measurement is just based on the CDF of the distributions. The KS test actually defines this distance, and it is defined as the largest gap between their CDF curves. So F1 is the CDF of the first distribution, F2 is the CDF of the second one, and we just compute their differences and then obtain the max one. Now we have transformed the signal in each day into a CDF, and we can define the distance of distributions. So we can apply clustering algorithm to mine the shape patterns. The clustering algorithm actually contains 2 phases. In the first phase, we apply dbScan to remove the outliers. An outlier emerges when a huge accident happens at the corresponding day. After the outliers are removed, we use hierarchical clustering to obtain the final shape patterns. So, in the previous step, we have clustered similar days together, and the distribution of a cluster can be estimated by the average of all the days in the cluster. The final distribution is a multi-nully distribution, each probability in the distribution actually corresponding to 1 minute in a day. So we can use this set PT to refer to this distribution. To get the baseline, we still need to expand this shape because they are all just probabilities. The expansion only needs to find the total traffic n for the day. If n is determined, multiplying n with the probabilities pt in the shape distribution will give the baseline. In order to get n, we need some sample from the day. Usually, we can get the prefix of the signal observations of the day. So, suppose yt is the prefix. Then, the best n should be the one that we can maximize the likelihood of perceiving the prefix yt based on the n and the shape distribution pt. So this probability. So when a multi-nully test is repeated by n times, the number of times that each outcome appears follows the multinomial distribution. We can prove that the best n in this multinomial distribution will be in this simple form. So in this simple form, the PT are actually the probabilities corresponding to those YT in the prefix, not all the PTs. So similar to linear regression, this formula is also susceptible to the abnormal points, right? So if we have abnormal points in the prefix, the n will be pushed away. So we also developed a robust version. In this version, we assume that the yt's are independent random variables, and each yt follows a distinct binomial distribution, and the binomial distribution is derived from the multinomial distribution. So using a number of deductions, we can prove that the best n is in the following form. So it's much complicated. And let me show you an example about the algorithm. Here is a traffic signal in one day from the last year, 2018. There is a segment in this signal which is a little bit lower than its normal level. A human engineer will feel very hard to find that which segment is the drop, right? So let me add the baseline here. We can clearly see that the segment starting from 18 o'clock to 22 o'clock is lower than the baseline. So far, we have 3 methods to compute the prediction values for the traffic signals, and we can apply Poisson distribution to detect anomalies. A data point in the traffic signal actually refers to the number of requests received or processed in the system in an interval. So this actually perfectly matches the definition of Poisson distribution. A Poisson distribution has a single parameter lambda, referring to the average number of events in the interval. For our traffic signal, the lambda is just the prediction value y hat t, and k is the observed value yt. So the anomaly detection essentially becomes to estimate the probability of observing a value less than yt or greater than yt. Because the computation cost of Poisson distribution is quite high when x is large, when y is large, we can estimate the probability by Gaussian distribution and use the z-score to replace the probability. So this is the z-score formula. Here, a negative z-score will correspond to the traffic drop, and a positive one will correspond to the traffic rise. So the figure at the right side actually demonstrates an application to our anomaly detection on a signal with periodic spikes. In the top figure, the blue curve is the signal, and the red curve is the baseline. And the baseline is generated by the robust linear regression algorithm. The bottom figure shows the z-score of the signal, and the z-score becomes flat comparing to the signal curve, right? So setting the threshold on the z-score is much easier. So we apply the algorithm on many signals and find that we had to set different threshold on z-scores for different signals. So we spent some time to study the reason, and the result is actually quite surprising. The Poisson distribution actually assumes that the incoming requests are independent to each other, but in the real data, this assumption does not hold. For example, many web pages embed JavaScript programs inside. So when the user performs a click on the page, the JavaScript program will generate multiple requests to the backend service. So in order to get around this issue, we assume that the observed traffic y is derived from a hidden true traffic x, and the value of yt is a constant c times the value of xt. Based on this assumption, we conclude that the z-score on y is expanded by the factor of the square root of c. This means that the variance of the z-score of yt is c instead of 1. So if there are no anomalies in the history data, we can directly compute the variance of the z-score to get c. Again, anomaly values just get in. So the robust version of the estimation of standard deviation is median absolute deviation. It can compute in this way. According to the Gaussian distribution, MAD, median of absolute deviation, correspond to the 75th percentile of the distribution. So this probability corresponds to this value. So we can estimate C based on this formula. So here are several applications of the anomaly detection algorithm. They are all for important signals. The first one is the traffic signal of Baidu's search engines. we not only need to detect the total traffic signal, but also need to detect sub-traffic signals coming from different provinces. This is the scenario that we need to perform normalization on the Z-score. The second and the third scenario are from Baidu's feed service. The second one is about the traffic model, traffic signal, and the third one is about the click ratio. We actually applied algorithm for errors on the click ratio. The fourth scenario is the advertisement income signal. This signal can be regarded as a constant times the underlying traffic signal, so we can apply the algorithm for traffic signal. The last two scenarios are about network monitoring. The fifth one is for the external network monitoring system, which measure the network connectivity from the users to our data centers. And the sixth one is for the data center networking monitoring. Because the probing is the major method for monitoring network connectivity, algorithm for errors is suitable here. Since our probing agents for external network is limited, data sometimes cause false alarms. So we also set a detection of the related services traffic signals when both the probing and the traffic report are abnormal and alert is generated. We confirm all the alerts with our reliability engineers to evaluate the effectiveness of our algorithm. In all 6 scenarios, we achieve more than 90% on both precision and the recall. So as a summary, I introduced our algorithm to detect anomalies on golden signals. The basic idea is from statistical analysis, and also we borrow some techniques in unsupervised learning. So that's all for my today's talk. Thank you very much.
Hello. 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 One question. So in Baidu's practice, how many signals in your system you are using in this way?
Okay. So we have used this algorithm on 2 different kind of scenarios. The first one is alerting. So for the search engine's traffic, actually we apply this algorithm on more than 30 signals.
30. Okay.
30. And then there's another scenario in which is actually a diagnosis.
Yeah.
So you can actually collect golden signals for every module of a service, right?
So
and then you can detect the anomaly on them. And when the system is in the failure state, you can tell which module might be the root cause, right? So in this case, we actually apply the algorithm on more than 900 signals.
900, so totally is 1,000 about.
Yeah.
So how many resources you are using to support this monitoring?
The only cost actually comes from the VAE because it needs a lot of training resources.
Yeah.
But the other algorithm actually costs much less. We only need maybe 100 machines to perform the online detection.
So, okay,
Yeah.
so for 1,000 monitoring points, you're using about 100 machines to support it.
Less than 100, maybe
okay.
just maybe 20 or something. I forget the number.
Okay, thank
Yeah.
you.
Yes.
How do you measure it? Do you do like, I don't know, a day or a week of classification and then you look back with I'm particularly interested in network monitoring. Then you look back, for example, with network engineers, or you do it reactively on the spot where you send alarm directly to the people in charge and then have the feedback from them that, oh, this alarm was useful or not, and then you can use that to tune your thresholds.
Right. Precision is easy to collect because we only need to confirm all the alerts to our engineers, right? But the recall is actually harder. We have a mechanism that we need to review the whole algorithm every 1 week and talk to the engineers about whether there are any missing alerts there. Yeah. So all of this data are actually come from the real production system. Yeah.
Hi, I have a question about the anomaly detection model. So
Yes.
do you take the duration of the anomaly into account? Because I understand that for the traffic anomaly detection, sometimes the peak is just temporary, then it may not mean anything. So do you take what is the duration for that peak into account?
Yeah, we do have a filtering step after that detection. Yeah. So in this talk, I only talk about how to decide the current point is abnormal or not, right? So there is a filtering step. For example, we said that we need to perceive, for example, 3 abnormal points in a 5-minute window in order to generate an alert. Yeah, we do have that, actually.
Thank you.
Yeah.
I have 2 questions. First out, I just wonder, what is the frequency that you update your model? Real time or T+1?
Rebuilding a model, actually, we do that for maybe once per month.
Once per month?
Yeah, yeah.
Well, then I just wonder, how do you deal with scenarios, just like if there is a major release of your of the system that you're monitoring next day?
Yeah, I
or
understand that.
maybe upcoming promotion, maybe 2 days later.
Right,
How do you
right.
deal with that?
Right. So for traffic model, this is the problem only for the traffic signal, right? Because for arrows and
not really only limited to traffic model, but
Yeah.
I think maybe a workload, maybe CPU consumption or memory consumption may be also influenced by that kind of things.
Okay, okay. So if there is a major release there, and we miss the chance to refresh the model, and then the algorithm will generate a lot of false alarms.
Yeah.
So in that time, we can just have a chance to refresh the model.
Okay.
Yeah.
So,
So
I guess
of course
you
you can reduce the frequency if the system releases is very frequent. Yeah.
Okay,
Yeah.
then I think you don't have very good solution.
Well, actually, the training is quite fast, so you can reduce the cycle of rebuilding the distribution to maybe 1 day or 2 days, I think. Yeah, because it's just, in our experience, 1 month is enough.
Really?
Yeah.
Okay.
One question. To build this model, what kind of library you use? Python or what exactly you use?
I'm sorry,
So to write the code, right? So when you build the model, is Python or TensorFlow or what kind of things you use?
VAE, right? So we use TensorFlow. Yeah.
Hi, so I don't know if you can actually reveal this, but so currently in Baidu, is this running like online?
Yes.
And is this the only system that's online? Or do you guys employ multiple systems that, because you said for the recall and precision, you guys actually compare that with the real alerts that network engineers get, right? So how?
Oh, no. We actually collect those alerts, and then we manually build a table, and then confirm this table to the engineers. There's no another system.
Okay, so you have multiple systems employed, and this is one of them.
Yeah, yeah.
Hi, thanks for the talk. Kind of tying into that same question, we talk a lot about SLOs and like the error budget, and if the error budget goes down too fast, then you alert. Do you also do that sort of alerting or just anomaly-based alerting?
Just anomaly-based alerting.
Okay,
Yeah.
thanks.
We'll just take one more question and then we'll wrap it up. Thanks.
Hi. If you have multiple signals, right, do you apply convolutions to convert into one signal and then apply your anomaly detection algorithm?
Yeah. So, I missed the question. I'm sorry.
So, if you have multiple signals, right, you apply convolutions to convert them to a one signal and then you apply your anomaly detection. And if we apply convolution, like what is the criteria? Should they be conditionally independent or dependent?
So you talk about the arrow signal.
Yeah.
So there are multiple signals inside. So can you repeat the question? I missed that the point.
If we have multiple signals, right, coming from different sources,
Uh-huh.
so some might be dependent and some might be independent.
Mm-hmm.
So in that case, if I want to generate one signal, I don't want to apply anomaly detection for every single signal individually.
Mm-hmm.
So I apply convolutions, so whichever they are dependent, right, I can convert them into one signal and then apply anomaly detection. Is that how you do it in your case?
I think it's not the way you think. When you have multiple different signals, right? So we have a batch of algorithms to deal with them. And I mentioned the errors is that because the errors actually depends on the traffic. So we combine two different signals together. But in the other three types of signals, they are actually all independent signals. So the only thing is that for different signals, we may need to define different threshold on the z-score. So we have to apply some kind of normalization on the z-score so that we can use a common threshold for all the signals. So this is the way. Did I answer your question?
Yeah, thank you.
Okay.
Thank you, Chen, for that great talk. Can we give him another round of applause, please?